Good afternoon, everyone. So I'll present my PhD project entitled Deep Convolutional Neural Networks for Detection of Cortical Dysplasia. It's a multicentric validation from 5 epilepsy centers across the globe. So before I jump into the specifics, I'll give a very brief introduction to cortical development and its malformations. So cortical development is a very intricately complex process that has several overlapping processes that begins with the fourth gestational. So at the fourth gestational week, we begin with neuronal proliferation and neurogenesis, which is followed closely by neuronal migration, where you have these newborn neurons that travel along the radial glia scaffold and find their final placement in the hexalaminar lamination of the cortex. And by week 28, you see that a hexalaminar organization of the cortex is present. But along any of these processes, you can have disruptions in cortical development, and they manifest as malformations of cortical development. And FCD is one of these malformations. That result from disruption of the neuronal proliferation. So our pathology of interest specifically is FCD type 2, which is characterized by abnormal dyslamination. When you compare it with the control, you see there's a lot of disruption of the tangential and radial dyslamination. And in absence of balloon cells, these are enlarged neuron cells with peripheral nuclei and a glassy cytoplasm. And in the presence of balloon cells, it's type 2. And there exists a pathological spectrum that ranges from subtle, where you have very microscopic anomalies that are not detectable by our current radiological techniques. And on the other side of the spectrum, you have gross lesions. And you can see a similar spectrum on the MRI as well. It's probably not very clear, but if you look at the lesion on the right, there's a lot of cortical thickening and atypical circular anomalies. But if you look at the lesion here, you can't really appreciate it's very subtle. So along this spectrum, you find different cases that have different degree of anomalies. So FCD is intrinsically epileptogenic. It's the main cause of drug-resistant neocortical epilepsy, but it is amenable to surgery if the lesion can be clearly localized. So a clear-cut lesion on the MRI is the strongest prognostic factor for postoperative seizure freedom, because if the lesion cannot be localized, the patient has to undergo invasive electrophysiological recordings. And complete resection of the lesion is associated with seizure freedom in up to 80% of the patients. There's been previous attempts at localizing the lesion using various voxel-based and surface-based methods. So with surface-based methods, a lot of them were semi-automated. They used machine learning, but there was a lot of manual QC. It involved extracting features based on gray matter density maps, relative intensity, and comparing and z-scoring the lesions with respect to a database of healthy controls. Sample sizes were small. The lesion was optimized for MRI positive, and features were mostly intensity-based, and they were not really optimized for small lesions. So with the advent of surface-based methods, which models the cortex as a 2D surface manifold, there was an increase in the diagnostic yield. The methods were automated. They used machine learning. The cohorts were mixed positive and negative MRI. And features were based on intensity morphology, where the 2D manifold was used to extract the features. But there was a lot of intensive data pre-processing in the terms of classifying the brain into white matter, gray matter, and CSF, and the surface extraction of the brain. And what was common to all these methods was that there was limited histopathological validation in the lesions, and no algorithm was validated on independent data set. It was usually within the same centers. So to overcome many of these shortcomings, we present an automated approach based on deep learning which learns increasingly complex representations with multiple levels of abstractions. That's the depth of the network, and doesn't rely on feature engineering. So to give you a brief description, here you can see that this is these convolutional neural networks have been compared to the information encoding in the ventral stream of the visual cortex. So you have the stimulus that goes through the retinal ganglion cells, the thalamus, and through visual areas and the inferior temporal cortex. So these neural activations in each of these layers can be compared to the different layers of the neural network, and these feature maps, which are basically derived from the convolution of the image, and they're basically linear and nonlinear units that learn increasingly complex features as you go through different layers. And we demonstrate generalizability of our algorithm using histologically verified lesions at 5 different sites. They're based on multi-contrast images, T1 and FLAIR. And we require minimal pre-processing and while operating directly on 3D MRI voxels. And we can get away with the surface extraction. So at the primary site, we had 40 patients with histologically confirmed F3 lesions. To demonstrate specificity, we used 38 age and sex-match healthy controls and 63 age sex-match temporal epilepsy with hippocampal sclerosis as disease controls. We collect multimodal isotropic data with 2 contrasts, T1 weighted MP rate and 3D FLAIR. We had minimal pre-processing. We had FLAIR and T1, which went through intensity normalization, inhomogeneity correction and normalization, followed by linear registration of T1 to the MNI 152 template, and then FLAIR is registered to that T1 template. And then we do the skull stripping. Interestingly, 80% of the patients that were initially reported were MRI negative, meaning that the initial exam of the MRI did not reveal the lesion. So in those cases, feature-focused location was established using intracranial EEG. The manual annotations were done by 2 experts who had a very high reliability agreement index, and we used the fusion of those 2 labels to perform the training. For the design, we compute sensitivity as the performance measure. If the lesion, so this is the lesion label, and this is the prediction. If they co-localize, that's the definition of a sensitivity. So at site 1, we perform 20 repetitions of 5-fold cross-validation, meaning that for every 32 patients we use for training, 8 were used for testing. And we made sure that all patients were tested, and then we had 20 trials for that. And for the cross-dataset validation, we used all the patients at site 1 to retrain the model. And the validation dataset composed of internal dataset. There were 8 patients basically from the site 1 that was the MNI, and independent dataset of 5 sites. And you can see there's quite a bit of variability in the scanners that we use. We had Siemens, GE, Philips, and then different variants of these manufacturers. And we had both 3D as well as 1.5 Tesla dataset. But the training was done entirely on Siemens TrioTIM 3T. To test specificity, the same model that was used to test independent data sites. We used the validation data set from site 1, which was composed of healthy controls, 38 healthy controls, and 63 disease controls. So we posed the lesion detection as a classification problem, which discriminates lesional from non-lesional tissues. So here we stack the T1 and FLAIR, and then we extract patches, because 40 patients is not a very large number to train the neural network. So for each voxel, we center a 3D patch of size 16 by 16 by 16, and then we pass it through the neural network that has 3 convolutional layers followed by max spooling. And then we have the softmax activation. And so we use this architecture, so 2 of these in tandem, to train our network. So here's the lesion label overlaid on the MRI. So we extract lesional and non-lesional patches. So the purpose of the first is to extract maximal lesional voxels so that we can have the highest lesional candidates to reduce basically the negative examples. And the second one is to maximize specificity so that we have least false positives. So since there's a lot of data imbalance in our data set because the lesion only represents 1% of the total data set. So for all the patches we collect from from the lesion, we match the same number of voxels by randomly sampling from rest of the brain. Here we use a crude gray matter mask extracted from FLAIR, and then we apply a conservative threshold at 0.1, and then again we do the thresholding. So once we have these trained models, we can use this test case. We extract the patches. It goes to the first trained model. We have this intermediate prediction that we threshold, and then in the second one, we have a more localized prediction. We threshold it. We do a series of erosions and dilations, and we compare it to the manual lesion label, and that comprises the sensitivity. For results, at the training side, so that was basically 20 repetitions of 5-fold cross-validation. We had 87% plus minus 4% sensitivity. Basically, on average, we detect 35 out of 40 lesions, and there's 2 plus minus 1 extra lesion clusters. For the validation data set, we had similar performance. We detect 89%, that's 39 out of 44 lesions, and with 4 plus minus 2 extra lesion clusters. And across different sites, it's pretty consistent. There's not one site that drives the average results. For the specificity, with healthy controls, we had 95% sensitivity, meaning only 2 of the controls had at least 1 false positive. And in TLE-HS patients, we had, so at least 6 of the 63 patients had at least 1 false positive. So we had pretty high sensitivity as well. So here you can see the prediction overlaid on the FLAIR contrast in the first row. Then you have the concomitant FLAIR and the T1. And these 4 last cases, they were actually AMRA negative to begin with. And our algorithm does pretty good job at detecting these lesions. So in summary, we achieved excellent sensitivity and specificity in histologically validated lesions, 60% of whom were initially overlooked on standard radiological exams. So our method represents 50% higher detection rate than conventional visual inspection. We demonstrate high generalizability using relatively small but diverse data sets. And this method can be easily integrated into clinical decision-making workflow with inference times of less than 6 minutes per case. Thank you.